Good afternoon, everyone. We are going to get started in a few minutes. Let me configure the things for recording. Okay, so hope you are able to understand everything, or at least some of it. So now what I am trying to do is present, no? Meet. Okay. So the today's topic is diffusion models. Okay. And we will look to that. This is the paper on diffusion, but we'll go by the review paper as I've shown previously, which is more intuitive. Then we'll get to this paper. Okay. And so the review paper is here it is. So I've shared all the required documents as well. Okay. So we have learned till VAE. Okay. And in VAE, what did we see? So in VAE, as you can see from the uh, slides I am presenting, so we needed to know the data distribution, which is PX. Okay. And for that, what we did, we got a proxy to maximize, which is called the expectation lower bound, what is called evidence lower bound, sorry. So evidence lower bound, so instead of maximizing the likelihood, which is log px, because we don't know px, okay, we maximize the proxy, that is evidence lower bound or elbow. Okay, you can see it from this diagram. So this expectation over log p x comma z and q phi z given x. Okay. And so this is the lower bound. You can maximize the lower bound and get the same result. Okay, the derivation is shown here. Okay. And now this elbow can also be written in two terms, which is one is reconstruction term and another is the prior matching term, or which is also a regularizer, type of regularizer. Okay. Prior matching, you can understand what does it mean, is it matching the true priors. Okay. One is q phi z given x, and another is pz. Okay, so pz we're trying to learn, and pq phi z given x is like the substitute for pz. Okay, so something like that. So q phi z given x is the encoder. Okay, we're trying to learn the encoder, and p theta x given z is the decoder. Okay, pz is the prior distribution. Okay, and these things you can see, these are also in the paper. Okay, how you calculate it, there is like for the maximizing of expectation you can approximately make it sum over the DKL term. The KL divergence term can be calculated algebraically. Means closed form solution is there. Okay, and that is shown in the paper as well. Okay, and this is the what do you call that, some uh, reparameterization trick that was shown. Okay, so in spite of sampling z, which makes the process non-differentiable, um, you sample epsilon. Okay, as epsilon is independent of the parameters of the two models, so you don't need to differentiate with respect to epsilon. Okay, so that makes the whole loop differentiable. Okay, so that's the important thing here. Any doubt here? Very low strength today. Abhishek joined here. So any doubt in up to this point? In exams, both coding or non-coding questions. I don't think there will be coding questions actually. I'm not too sure actually. I will not be the question maker. Uh, any doubt up to VAE? Have you understood VAE? Because the diffusion model that we're going to see actually builds on VAE. So just a recap I have done. Any doubt, then we can discuss more. Is it clear for everybody? Ujjwal, Sunanda, Shubhankar, Madhukumaran, Iyer, Bhavya. Any doubt? So Bhavya, we have just discussed, means recapped the variation autoencoder. Okay, so you have missed that part. Okay, that's okay. But if you have any doubt in understanding VAE, we can take it again, or some part of it, or whatever. No doubt, huh?
Uh, Excuse me, Nirban.
Yes.
Uh, Actually, I was having the same doubt which Shubhankar was having, that like in our assignments, there are many coding questions, and I think every second or third assignment is of coding. So for now, the pattern is clear. If we do the coding questions, like we just have to complete the code and get the output and take the correct one. But how this will be in the paper, that I am not able to understand. Like, can you please guide on this?
Uh,
Yes, I have the
Yes,
same
sir.
doubt.
That was only my doubt.
Yeah, I have the
Because
same.
I'm new to this. Like I'm not like I don't know anyone who has taken this subject previously. Like how the questions actually comes. Do we have to code or do we have to solve the numericals?
Yeah, same.
uh, I think if it comes, means I'm not going to make the question actually. That's why I don't know actually. But if it comes, it is going to be of similar pattern, I think. But most probably in most of the NPTEL course, you don't get the exam with coding questions. It's mostly theoretical questions only. Okay, so but as I'm not making the questions, I cannot be sure. Okay, but 90% sure that there are going to be no coding questions. But coding is important to learn it. Okay.
Sir, but we need to prepare coding also, right? For exam.
Uh, how can I? So you need a sure answer, huh? Oh, how can I give a sure answer if I don't know myself properly? But I have done for many courses. In none of the courses people give coding questions.
Sir, are there any previous year questions available so we can get an idea and prepare better? Because you see, 50 to 40 to 50% of the assignments are based on this IPv4 file we are getting, where there are code snippets that we need to write and then run. And this can be done, when we have Wi-Fi connection, because we need to run it in a Google Colab notebook. So
Mm-hmm.
that thing in as we can visualize a paper of NPTEL MOOC course. So Wi-Fi connection and switching the tabs might not be the way we would proceed in the examination. So that's why the conflict was happening whether we will actually get coding questions or not.
Okay. So to be totally honest, I'm not sure whether there will be coding question, but I'm quite 90% sure that there will be no coding questions. I can tell you that, but I cannot guarantee for the rest of the 10%.
Okay, all
Anirban,
right.
just a small question. Like,
Sir,
okay, like if
then can you please tell like can we get the previous year question paper or where can we search for that?
Okay, I'll try to see. Yeah, I'll try to. If I can give you in next class, that will be okay, right?
Okay, sir. Okay.
Okay.
Thank you.
Thank you, sir. And if you could just um, get the information of whether we'll get coding questions or not, it will be really
Okay,
great,
I
helpful.
will check that as well. Yeah, yeah, I can do that.
Thanks. Yeah.
Okay.
Anirban, I was just saying that, like, if in case like we don't get the coding question, so like we will also like to know like how to approach those questions or how to prepare for those questions, because there are a lot of questions which are under this category, and if they don't come, so practicing like how to practice those questions, because otherwise a lot of questions will be
Okay, so you
skipped.
are struggling with the
Point.
theoretical part.
Theoretical part, I think, yeah, it is also a bit difficult, but I think that's doable. I'm more struggling on the coding part, like,
Coding
because
part. Okay.
yeah, because I'm not having that background in deep learning, so
Okay.
that's why.
So what are the other TAs are showing the codes, right? Well, I haven't done that.
Other, sorry.
Other TAs that you have in this course, they are showing the code solution as well, right?
Actually, I have not joined the previous meeting, so I don't have any idea. Anyone who has joined the previous meetings might have a
Means
bit
for
about it.
other TAs, means like other three TAs are there, right, in this course. So if they are showing the coding solutions, you can refer to that.
Can, can you specify what do you mean by TA exactly?
So I'm actually a TA here in this course. So I'm a teaching assistant. Okay.
Oh, right, of
Yeah.
course.
So there are three more teaching assistants. Okay, if I can tell their name. So
Yeah, and if you could just send the email ID or something so that we can contact them.
so the thing is that in the okay, let me show you. So you can see my browser, and what I'm going to search. Okay, so cannot log in here. So what I'm going to do now is that I'm going to present from here. Okay, means that I have two devices to teach. Okay, uh, so I'm going to present from the another one. Okay, so I cannot log in on the other one. So you can see right now another presentation I have done, another screen share from the another login. Means you can see the survey and problem solving sessions. can respond.
Yeah,
Yeah.
yeah, exactly.
Yes, Anirban.
Yeah. So in the bottom of that, oh, this is survey. Okay. So this is the course list. Okay, and you can see the problem solving session recording is there. Okay, so you go there. Okay, and you can go to this point, and you can see all the videos that were recorded are here. Okay, so I'm one of the T. I'm Anirban Rai here, and there is Avin Dayal, Manogna S, and Ayush Kumar Tyagi. Okay, I think Ayush does show his coding coding things as well. So let's see. Yeah, so as you can see, he is sharing the codes as well. So I haven't done that. I was really busy. Okay, but you can refer to these codes. Okay, so this VA codes and all are there. It's from the week 10, right? So I think he has coded it out, as you can see. Okay, you can see the codes, right? Yeah,
Yeah, we can.
training and everything. So you can refer to these. Okay.
So, is there any rough estimation of what kind of questions are gonna be more prominent in the exam, like the ratio of numerical theory and codes?
Usually theory is the one that comes in all of this NPTEL exams. But I will make sure. Yeah. So the two questions I have to answer is what type of questions come, and previous year questions if there is. Okay.
Yeah, and the common doubt was that the coding part is gonna come or not, and how will
Yeah.
it come? This is
Yeah.
the common doubt. Yeah.
Yeah. So I'll try to clear that one on the next. But for now,
Anirban, one request is there. If you get the answer from whosoever is concerned, so you can also please post in that discussion group which is there for us, like so that information reaches us as soon as possible.
I don't know which discussion group. So is it WhatsApp group?
No, it's not a WhatsApp group, but it's a discussion forum which has been made for deep learning only. If you will go on the homepage, you will see it's there only.
Here,
At the top, Q&A,
Q&A.
and at the top, in the navigation bar, Q&A, adjacent to about course.
Okay, okay, yeah, yeah. It's there. Yeah. Oh, okay.
Yeah, so if in case you get the information early, so please kindly post it over here so that we can prepare accordingly because the date is approaching fastly.
Yeah, I can also see the top comment is about the coding questions itself.
Yes.
Yes.
Okay, okay, yeah. But I didn't know this one. Yeah, I'll reply on this thing. Okay. Yeah.
So we will actively checking, like we will keep on checking this group actively as soon as you will post some updates. So it will help us a lot.
Okay. Yeah. Sure.
Yeah.
Yeah. The doubts and everything are here. Any TA is active here?
Yes, I don't know whether they are TAs or not, but generally we get the answers from here, like whosoever is concerned.
Okay.
Yeah, also, I think someone has shared this group link also in the comment section. I'll just make a list of whatever doubts we had, these two, three doubts, and then it'll be easy for us to keep track of it.
Okay. Thanks. Didn't know about this.
Anirban, can you please also share your email ID, like if
Okay.
in case uh, we can have a follow up.
Drive link. Okay, I'll do that as well. But you can find the drive link in the course page itself. There, put my email address and they are here. So share that as well. Okay. So you cannot access recordings or something. You did not were not able to before. So everything is done now.
Uh, yes, I think. But please just get back to us as soon as possible
Yeah,
whenever you
I'll
get.
just post this list I'm making as I said. So just a second, give me a minute.
Which list you're talking about? Acha, in a doubt only.
Yeah, it's best to create a doubt thread on that only if you reply. So it's good.
Yeah,
Everything will be there only.
yeah, do that. Okay. Uh, so what was
Yeah,
I saying?
posted in the comment section.
In the comment section here. Huh? No. Where is it? Which comments?
The in-call messages of one second.
Bhavya, just post it in that discussion forum. I think it will be
Yeah,
better.
I'll do that. I'll do that.
Okay. Okay, Abhishek.
Anirban, one thing I wanted to ask, like, actually, deep learning is a bit new for me,
Yeah,
and
it's
I
quite new.
don't, yeah, so I don't have much background in this deep learning and all. So I just wanted to ask, like, if I just like do the assignments thoroughly, so like, will that be enough to pass the NPTEL course? Because actually, I'm currently working in a company also, so I get very limited time to study, and that too, it's a very new subject for me.
Sure.
And corresponding to it, I'm also doing three other MOOC courses which my college has asked me to do. So, so that's why I was just asking, like, will it be enough to do the assignments to just pass this course?
Uh, it should be enough, yeah. But like doing the assignment does require knowledge there. Yeah.
Yeah, actually, I have the same concern with the um, work culture and the balance. So, will it be enough for us to do the assignments apart from the coding questions, like just the assignments of numericals and theory itself?
I mean, if you do all the questions, you should be able to pass. You know that's the thing. But doing all the
Apart
questions
from
does require
coding.
knowledge. You know.
Yeah, I mean, we were, kind of thinking of skipping the coding part, to be
Just
honest.
skipping
So
the
that,
coding part. Now this
yeah, because 5 to 6 assignments are based on coding. So that's what we are deciding to skip. So is it the right way to?
no, it is not the right way. You know, passing exams or what, but like without coding the theory we have learned, it is very hard to learn anything. Because deep learning is like an empirical subject. You know, it is not like just theory. You know, do have to implement once. You know, it is a very practical subject. So you have to do the things that are required to be done.
Okay.
Yeah, it is not advisable to skip, but like it is not advisable to skip because you know the clarity you get with coding. I mean, it's like the VA I told this function and this function, this distribution sample from this. You know, what does it look like in coding? That's the question. Maybe I can show you that. So up to this point, you understood VA. You know, which part was clear? I think someone asked the latent dimension part. Okay, so uh, when I showed when I presented that one, the survey paper from which I explained the VA. So did anybody have any doubt? I think latent representation was some doubt there. So we'll look at the code to understand better, and you will see that you know it's so much easier with the code actually. Uh, and any other doubt actually from it? I mean, let me show you here only. So so while it is up, okay, so let's try to understand the VAE. Okay, so the input dimension, as you can see, 784. So what does it mean? That you have the image, you flattened it out into 784. You can understood, right? um, First row, then first row as a vector, then second row, third row, like that, and you can flatten it out into 784. So is this the one? It is not the one. uh, so uh, so let's understand. Okay, so you wanted to understand this latent dimension, right? And this hidden dimension as well. Okay, so what is the hidden dimension here? So there are two types of dimension he has defined. So this is from another TA. Actually, I have not written the code actually. This is from Ayush. Okay. Uh, so uh, so as you can see in encoder, hidden dimension and latent dimension is defined two dimensions, but I'm not sure about. Oh, okay. So what he's doing is actually, so this latent dimension is the final Z that you see in the paper, okay? But he's actually doing it in two steps, not in one step, okay? So what happens if you encode into a very small latent dimension, which is 20 is very less. Sometimes the information is lost, so it is doing in two steps to preserve the information, okay? So first from input dimension to hidden dimension to latent dimension, and another. So so what it is doing at first, it is means using one linear layer uh, to encode from 784 to 400, and then it is actually learning the mean and variance. um, so um well, I can but it is my easier in my iPad actually, because I cannot do anything here. It is 2 given in the function argument. Okay, okay, it is a type of the question. Okay. Okay. So what I'm going to do, I'm going to present from my iPad only. uh, then it is easier for me.
Hi, Nirpan. I've just posted the group link in the in call messages so
Okay,
that we can follow
got it.
the thread.
Saw it
Thanks.
there. And so Swayam, yeah. Oh, I cannot log in here. Oh my god. Okay, let's come back to the laptop. Yeah. So uh, okay, I was going to show the. I need the review paper. Yeah. So review paper. So I've shared all the papers in that Google sheet that I've shown. Okay, I've shared all the papers there. So this is the one. This is the Calvin Luo. Okay, I get the name wrong, so I'm not able to search. Okay, so what did we see here? That it is also in the presentation I had shown. Okay, So what they do is they sample from a 0 1 normal distribution, then from the encoder they get the mu and sigma value, and then they final make the z that is to be fed into the uh, this decoder. Okay, so that has to be done. Okay, and now, so this was the code. Okay, so from these two networks it gets the mean and log vr variance that it has written, so you can take anti-log and get the variance. Okay, so the decoder, what does it do? So decoder is defined as two layers. Okay, here, and you can see the flow of the information. So the first this layer, it is fed to the age you can get, and then from that you can get the mean and log variance. Okay, and that is the encoder here. Decoder, if you see, it takes the z, and z, how do you get? So this is the z. Okay, so if you can see, z will be so whichever is calling the reparameterized one. So let's see the training one. Okay, so here so data is there, optimizer reconstructed. Okay. Okay, so what it is calling here, model. We do need to define the model as well. Okay, model is passed here. So wherever it is calling train VA, so as you can see, the train VA is called here. So first they define the model as this. Okay, even more reducing the latent dimension here. I don't know if that is a good idea. And now you call the train VA, which puts the model there. Okay, which is the VA model here. And when you go to train VA here, uh, go to train VAE. Okay, so this is the script for training. Okay, and here so it is putting the data there. Okay, so data is the 784 dimensional, and it is a mean, log VR, and reconstructed is being output here. And okay, so this is the three outputs that you're getting. So reconstruction is like the decode z. Okay, and z is the reparameterized one. Okay, so first this mean and log VR that you get from the encoder is put into this, and you get the output. This is the z. Okay, so this z you get here, and you put z into the decoder. You can see the structure of the decoder. Okay, one linear layer, then ReLU, and then another linear layer, then sigmoid. Okay, and that way you get the output. Okay, so okay, so here you can get the reconstructed one. So in loss, what you will do, you compare the original data and the reconstructed data. Okay, so data and reconstructed will be compared in the VAE loss. Okay, so here as you can see, in VAE loss is reconstructed and original. You take the, so they have taken the cross entropy loss for comparing. Okay, and also you need the KL divergence loss. Okay, so if you can see here, so there are two type of losses here. So first is this reconstruction loss, and another is the KL divergence loss. Okay, so you need both here. So both are calculated here, and you add them together, you get the and return it. Okay, any doubt? So this is the flow. You very well understand with the how the VAE works with this code. some plotting is also there. So visualize reconstruction. I think then visualize both the data, then you can compare. I think something like that. Visualize each color represent different digits. So you can see this MNIST one as well. Okay. So any doubt here? So the theory that we have seen, you can see the implementation as well. Okay. Okay. Uh, yeah, Iyer has said that. So latent dimension VA. Okay. So you understand, means like latent dimension is like so the original dimension is there. Okay. Original space of the image is there, and you're encoding into a latent dimension. So what does it mean is that you are taking it to lower dimension space. So what does it help here? So first thing, why it is necessary, because we were not able to learn the distribution of the data, input distribution with just because the px log px, the log likelihood was not possible to minimize, not possible to maximize, because we did not know px. Okay. And for that the z was introduced, which is a latent variable in a reduced space. Okay. So it helps us to learn the original distribution through a proxy called elbow. Okay. Any doubt? Any doubt here? Anything missed? Because we will build on this. Okay. Does the latent dimension to number of attributes? No. Latent dimension has is chosen by the modeler, whoever is coding it out, based on requirement. If you take, so if the latent dimension is too small, what happens is that the information holding capacity of the dimension is small. Okay. So you can lose information. If it's too large, then it will be computationally expensive. So the benefit of using a latent dimension, you lose in that. Okay. So it should be just right. If it's too small, you lose information. So that's really bad. Okay. If it is too much, then it is computationally heavy. Okay. Yeah. Any more doubt? Oh my god. Any more doubt? No doubt, right? So you can check the codes, but I have not written the codes. Okay. So you can attend the sessions of Ayush as well, or you can just check his code, whatever works. Maybe I will code, but running very busy these days. Okay. So what was I going to do? We were going to, where do we get the codes? So the codes are in the problem solving sessions at the bottom of the, so you can see here. So here there is problem solving sessions. Okay. Session recording. So you go there, so this opens up, and Ayush is at the bottom. So this presentation folder link, so you can get the lectures, whatever course and everything, whatever there, and there is a YouTube video links as well. So I'm at the top here. Okay. This is it. Okay. You can find from here. I'm surprising you did not know that actually. You can find the recorded lectures here. Everything is here. Okay. So I will switch back to my iPad here. Easier for me to teach there. do here, so this is the hierarchical variation or autoencoder. So in hierarchical variation autoencoder, what happens? So we build on hierarchical variation, first variation autoencoder. Variation autoencoder multiple used multiple times in hierarchical variation autoencoder. We put some limit restrictions on it further, then it becomes a diffusion model. Okay, so that is the structure here. So as you can see, so there are multiple latent states here. Achha, so what we saw here, no, but that was not hierarchical, because at every step you need to calculate the mu and sigma. Because I was saying that in that code you see na, there were two latent dimension, okay, but that was not hierarchical, because at every step you need to calculate mu and sigma. Only once there was mu and sigma. Okay, so this is the hierarchical one. Okay, and so they have written this joint distribution, what we saw previously as well, in this form. Okay, so they take the Markovian assumption that every state transition probability is only dependent on the previous state. Okay, so this p theta z, so as you can see, this p theta, okay, this p theta z, so z t minus 1 only depends on the zt. Okay, so what we are seeing here, let's try to understand better. So first what we are doing is that you are going to this latent dimension z1 through the process q z1 given x, then subsequently to subsequent q's, and then you're reversing as well. Okay, and reversing is, you can say it like reconstruction. Okay, that we had seen before, right? So suppose z t minus 1, capital T minus 1 is the image you have. Okay, so you move to z t, so that is the, like in the variation autoencoder, z t is the z. Okay, then you reverse back z t to z t minus 1, so that is the reconstruction, you get the image back. So you do it multiple times actually, so that is how it is. And these equations are very much valid. Can you understand this equation, how they are derived? So what happens is that you do pzt, so that you take this term first, and then what you do pzt given what comes here, zt minus 1 z and zt minus 2 dot z 1, and then x, like that. And now zt minus 1 is only dependent on zt is only dependent on zt minus 1, right? So you can write it like this. Okay, so it goes on like this and you get the answer. Is the p, right? So I've done it for q, I think. So you can see, so it is the Markovian assumption, the derivation you can see. So the thing is that so the structure that this multiplication structure we get because of the Markovian assumption. Okay, and you again do the elbow thing. Okay, so and this elbow can be written when you put the two distributions here, and then you get this form. Okay, and now we get to the variational diffusion models. Okay, so the very different thing is that the latent dimension is exactly equals to the data dimension. Okay, so in VAE what we saw, the latent dimension is the reduced space. Okay, but in diffusion models it is the same space. Okay, it's a very important thing here. Okay, the structure of the latent code at each time step is not learned, another very important point. Okay, so the latent the structure of the latent encoder, okay, is not learned, it is predefined as a linear Gaussian model. Okay, so what it is, this distribution that when you are doing this, these are not learned. Okay, the The structure is not learned. What type of distribution it is not learned. It is already defined. I define it like a Gaussian distribution centered around the output of the previous time step. Okay. So the mean is the output of the previous time step. Okay. Mean of the Gaussian. Okay. So that is given for us. The Gaussian parameters of the latent encode vary over time in such a way that the distribution of the latent and final times step t is a standard Gaussian. Okay. So the interesting thing is that this xt becomes normal distribution 0 1 at the final time step. Okay. So this is something. This is normal distribution. This is some mu and sigma. So it changes in such a way that you get a normal distribution 0 1 at the end. Okay, so that is a very important fact to notice here. Okay, able to understand it out up to this point? And this is called the forward process. Okay, and this is called the backward process. So so this research was a quite legendary research. It was done in the lab of Peter Abel. Okay, Jonathan Ho leading the research here. It was a groundbreaking paper, still is, because the diffusion are the models for high quality generation you get from this. Okay. Uh, so what they show, what we further need to understand, it is like seen as adding small noises at every step until it's get totally noisy, and you can say it like it is a 0 1 normal distribution. It's not like random. In noise there is randomness, of course, but the structure is 0 1 normal distribution, right? That like it is sampled from a 0 1 normal distribution. Okay, so that's the important thing here. So there are a lot of things here. Let's understand that. Okay. So the first thing is that let me now go to the paper. Okay. This is the DDPM paper. The high quality generation, as you can see. So as you can see, the author Peter Abel, Jonathan Ho, Ajay Jain. Okay. Jonathan Ho and Ajay Jain are still a PhD student. This is not a very old paper. Okay. And so high quality generation, as you can see, celebrity pictures. Okay. So what do we do here? So this is called the forward process, which is shown in backward actually. I know that. So this is the backward process. Okay. I hope I'm correct. I should not say wrong. Let me check. Yeah. So I've seen. So this is the reverse process actually. Denoising the image is the reverse process, and noising it is the forward process. So best thing we have to see here is that the noising process, you don't have to learn any parameter. The distribution is already defined. You keep adding noise. Okay, it is a normal distribution, and you condition it like that. X capital T is a simple standard normal Gaussian distribution. Okay, standard normal distribution. Okay, but the learning part is in the denoising part. Okay, not in the noising part. And so the derivation and everything are still the same. So this is the likelihood you have. You can write it like this. Okay, this x0 is the input image. Okay, and these are the latents x1 to xt. Because they are the same dimension, you write it as x, okay, not as z. Okay, so one demerit of this diffusion model is that you are calculating in the original data space, which is computationally expensive. Okay, and so that was a very crucial demerit of this diffusion model. Okay, so but they were able to subsequently people were able to model them as a latent diffusion model. So what does latent diffusion model do? They use a variation autoencoder to get to a latent space, and then they use a diffusion, okay, inside that latent space. Because in diffusion model you don't get to a lower dimensional space, which is the problem. Okay, but we don't get to that. We are working in the same dimension. Okay, so as you can see, latents of the same dimensionality as the data. The joint distribution P theta x 0 comma t is called the reverse process, and it is defined as a Markov chain with learned Gaussian transition. So these are the thing. Okay, so you can write it as transition like this. Okay, this joint distribution, and this joint distribution with this transition. Okay, so this is a denoising step. Okay, so you don't know mu theta and epsilon theta. Okay, we need to learn that. Okay, and this transition from x so this joint distribution is written as this. Okay, this is the forward process one. Okay, noising step. Okay, and it is written as like this. Okay, and so the cool thing here is that in the noising step you don't need to learn anything. Okay, this beta is not like you need to learn here. This beta is already defined. Okay, so beta, the forward process variance beta t, can be learned by reparameterization or held as a constant hyperparameter. Okay, and we have seen that if you can hold it as a constant hyperparameter, it works well. Okay, so you don't need to learn it. Okay, okay, so beta t is actually defined as a time based variable. Like you can take it like a linear what do you call that, geometric series. And so in this geometric series and what type of series, it's kind of arithmetic progression. You can take it like arithmetic progression, something like that. Okay, and and you can, so the alpha, so with time it is varying. Beta is like something, suppose from 0.1 it is varying to 0.11 in 100 times step. You can divide it with equal increase at okay, so you can make it arithmetic progression like that. And alpha t is defined like this. Okay, now so this so one thing is that in place of like transitions one step and after another in this forward process, because forward process is not learned, it is defined by the user. So what they do is that they do not do it like one after another, because they have then because we have already all the knowledge, you can model it like one step. Okay, so that helps during inference. Okay, during training you do have to do transition, but during inference you don't have to do step by step. You can just use this formula. Okay, so that is there. This is the loss function here. uh, okay, so details are there for further simplifying the loss function. And now, so this calculation they have done. Okay, for the forward process, this transition, okay, is defined like this. Okay, the calculations are there in the review paper as well. Okay, so forward process is, as you can see, very simple. Didn't have to write much because it is all defined. Okay, but the reverse process is where the learning is. Okay, so so this is the loss, squared error loss. So you simplify it to a squared error loss. Okay, and so this is the first we have seen the loss function, big one. So simplifies to a squared error loss eventually. In terms of mean you can write. Okay, another is that you can write in terms of this noise. Okay, so in the noising process you are adding sampling with this epsilon. Okay, so you can learn this noise. Okay, so this is while implementing I've seen the easiest way to do it. You don't need to write these things. Okay, why? Because for mathematical accuracy these are important, for because when you are back propagating, okay, the amount of the loss doesn't matter, it's just you have to come with the structure. Okay, and so you can we used to just calculate this epsilon minus epsilon theta squared error, and that's it. That works. Okay, uh, you can also write it in terms of x. Okay, so in the review paper you see all three derivations. Those are not important to see. Okay, so this is the easiest one. We've done it. So one is the 0 1 normal that you sample from, and another is this learned e theta one. Okay, so you need a neural network for learning it. Okay, so it does it. Okay, and so how does this parameter comes? Okay, so that is the derivation. How does it come? Okay, if you have learned epsilon theta, if you learn so that means you've learned theta. So you've learned the parameter of the forward process, reverse process, denoising process. Okay, and with that, in inference, what you can do, you take a noised up example with this. Okay, and then you denoise it step by step using the loss, using the transitions defined here. So transition, as you can see, so algorithm, as you can see, so this one works. Okay, you need this as the loss function, and then sampling step. So for during inference, as you can see, we're starting from xt, the totally noised one, and then you can get xt minus 1, xt minus 2, xt that like x0. Okay, so that's how this paper is done. So it's a very important paper. Okay, other a lot of details are there, but those are not important. Okay, any doubt? I am sure you'll have a lot of doubt, because I've told a lot of things, this and this, that, how it is done, but really going to the depth of it is a challenge in diffusion. So, importance of sampling here. Okay, so importance of sampling is same as in diffusion. Means in VAE, we are sampling from 0 1 normal distribution. Okay, and then what we are doing, we are creating the latent variable. Now here what we have, the latent variable, the structure of the latent variable is already defined. Okay, but you do need the noise, this sampling the noise to add to the when the original image is there, then you noise it up with some z0 comma 1, means with some noise, and then subsequently more and more noise. Okay, so we do that. Okay, so that is the same, similar to VAE. Okay, VAE, what we had, VAE, what did you have is that in VAE you don't need to what was I saying, we do it only once. Okay, but if in the forward process of this noising, you do need to do it multiple times. Okay, and we're adding the noise here. In VAE, when you sample it, you get the mu and sigma, and then you make an z. Okay, and then use it for decoding. Okay, but you here we already know the structure. Okay, so you only need the noise part. Okay, others mu and sigma are all taken care of. Okay, because the structure of the distribution is already known here. Okay, so that's the important thing. Any doubt? It cannot be so clear that if you're silent. IR Devosmita Muthukumaran Sunandita. IR. Yeah. Any doubt? Other people have left. They're only worried about exam, I think. other doubt? Should not be that simple. You're all silent. Denoising part. Yeah, I moved really quickly here. So reverse process, as you can see. So what we are doing is that, so we need to learn this distribution. Okay, so then for every step t, you can do it, and for learning it you need mu theta and sigma theta. Okay, now so first they model it like a independent. Okay, uh, okay, so matrix can be written as like identity matrix times some sigma t square. For every time step, sigma t is different. Okay, means, okay, means the sigma is dependent on the time t, but not any other thing. So untrained time dependent constant. It's dependent on time still. Okay, and experimentally both sigma t square equals to beta t, and so they do this, they try with this sigma t square equals to beta t, they try. Okay, another is the sigma t square is equals to beta t is equals to, okay, another so what it means is that they use this in place of beta t. So they were two values of sigma t they tried. Okay, so that's how it is. Okay, and now you have to understand this for comparing so you have to compare two images. Okay, so this the prediction, the what you predict, okay, is the mean of the image. Okay, so the value that of the image, the pixel values are actually the mean values. Okay, so that is why they define a squared error loss between the means here. Okay, now they're simplifying, so they're simplifying here, and you end up with this. Okay, so this loss can be written as this. Okay, so mu theta has to be learned, and xt, you know, xt, so they further simplify it down. Okay, and xt also they use it here, so they put everything and they get in the form of epsilon, which is the easier way to do it. Okay, comparing the mean is not easy. Okay, epsilon is what, a sample from the 0 1 normal distribution, and epsilon theta should try to match that 0 1 normal distribution. So what it is actually doing, you can understand. So what we are doing is that epsilon okay, so we were sampling from epsilon, and one sample from this represent xt here. Okay, and now when you're doing this, okay, from the image to this, you're also adding noise like that. Okay, and that adding noise is epsilon theta. Okay, so these two needs to be same. Okay, means we keep adding noise. So I mentioned before, you keep adding noise, the final image that you get is a sample from the 0 1 normal distribution, should be like that. Okay, so you compare what you know as a 0 1 normal distribution and what we get from the learning process, you compare both. Okay, so this is not known, let's say x, so you compare both. So they do it with squared error loss. So this has been done. Okay, so this is the thing. They tried to match, but if it is not matched, then what error? Then what error generates? So that is the loss. That is the error that we try to minimize. Okay, so they if you are able to make it close. Okay, so then we have trained the model. So what does it mean, make it close? It may reduce it so as much as possible till convergence. What does convergence mean? So in training any neural network model, suppose the loss doesn't reduce more than 10 to the power minus 5, then it is convergence. Okay, that is convergence. The two are um, the difference between the two, epsilon and epsilon theta, becomes less than 10 to the power minus 5. Okay, you have converged. Okay, so that's a very small difference, right? So you've learned the noising process. So what in the denoising process, what you are actually trying to learn is the noising process. मतलब ऐसा है कि you're trying to reverse engineer something. Okay, so that is so you start from the last and you move towards like that. Okay, so reverse engineering is what is diffusion. Any doubt? Any other doubt anybody has? Sunanda, Nagavani, Muthu Kumaran, Devosmita, Iyer. Any other doubt? No doubt, right? So let's move to the questions part. Okay, so what is a valid transition matrix, they ask. Okay, so what do we have to do here? Not able to write. Mm. So for valid transition matrix, what do we do? Oh my god. Okay. So where is it? Shared, browse, week 11. So for valid transition matrix, all entries of the matrix has to be positive or 0, is non-negative. And another thing is the row has to sum to 1. Okay, so that is the condition for a Markov, to have a transition matrix for Markov process. Okay. So that is it. You can do it. Which of the following forward process diffusion kernel will converge to a Gaussian distribution? So it is so hard to read here. So linear or cosine schedule, whatever schedule you use, it works out. Okay, so there you will not have any problem. So here they have used two things. One is Poisson and Dirichlet, and another is the normal distribution in the two. So they are linearly reducing it, and another is the cosine schedule they have written. As far as I know, both works out. Okay, and now if we're using different distribution, of course, will not converge to a Gaussian. I think top two should be the answer. DDP explicitly learns to true score function concerning the data distribution. So we haven't seen this one, score and guidance. Okay, we can do it in the next class. Do not expect it does not explicitly learn, so that is why it is a topic. And so first is correct. Generic distribution can be designed using stochastic differential equation based on the Wiener process. This is correct. These two are correct. Diffusion model based on ancestral sampling in the forward process. That is correct. One learns score of advertisement of a forward decision process. No. Correct everything and whatever. Oh, I got it A, B, C, which are the false. A, C, D. A is false. Directly the domain of the data itself. How is it false? It learns the distribution after all, so it should generate in there. They are talking about it generalizes to other one. Ancestral sampling in the forward process. That is on the correct. I don't know what it is. I'm very tired actually. So this is the calculation they have shown. Calculation they need here. So that beta and how the forward process happens. The calculation is here. So the variance is calculated like this. Okay, so you solve it and you get t. While training diffusion models, does the learning remain invariant of the weights of the reverse process? So it is correct because it doesn't have any weight. Actually, it doesn't have any weight to update. What did I see? Actually, reverse process. Okay. So in the forward process, it doesn't have any weights, but in reverse process, it does have. So it is no. Parameterized by neural network. So reverse process is the learning part, right? We have shown denoising step. Okay. Okay. So you can see the questions in details. Okay. The solutions are also there. Okay. Okay. We'll stop it now. Okay. Okay. I'm a little busy these days. Okay. Thank you very much. Transformer related paper.
করে দিবি।